Hello students, welcome back to my YouTube channel. In this video, I am going to discuss about magnetic field produced by a current carrying circular loop. First of all, we will do a quick review of the theory, then we will go to the problems. Current carrying circular loop produces magnetic field. So, I am going to consider a current carrying circular loop of radius r carries a current I. Okay, a point P which is at a distance x from the center of the current carrying circular loop, and this P is along the axis. Then the magnetic field at the point P is mu 0 I by 2 r square divided by r square plus x square all power 3 by 2. Okay, then if this point is at the center, then the magnetic field at the center of a circular loop is mu 0 I by 2r. Okay, then you see that the direction of the magnetic field can be found out by using right hand rule. Okay, so this is the thing. Y is a plane. Okay, so now you see that this circular loop is along the YZ plane, then the magnetic field you can find out by right hand rule. So I'll curl my palm in the direction of current, then the thumb will give the magnetic field direction, so that is along the x-axis. Okay, this is the magnetic field direction. So here you can write it as I cap, here also you can write it as I cap. Okay, this is the direction of the magnetic field. Okay, then here if the circular loop is like this, what about the magnetic field? Okay, the current is going in this direction, so the magnetic field direction can be found out by right hand rule. Cover your palm in the direction of current like this, the thumb is in the upward direction, so the magnetic field is like this. Okay, then if the circular loop is like this, the current is in this direction, so apply the palm is curled in this direction, magnetic field is downward. Okay, so this is the thing. Okay, this is the magnetic field direction. Clear? Okay, then if the loop is not a circular in shape, it is just a curve, then what about the magnetic field at the center? That we will see now. Okay, so I am taking a curve. This is a curve. This curve is making an angle alpha at the center. Okay, so the current is going in this direction. The magnetic field at the point O is mu 0 I by 4 pi r. The radius is r. Okay, r into alpha. Okay, so the direction can be found out by right hand rule. Curl your palm in the direction of current, then the thumb rule gives. Okay, clear? Then now you see. Then if it is a semicircular loop, what about the magnetic field? This is the center of, so this radius is r. Okay, then magnetic field at the center is mu 0 I by 4 pi r into alpha. Alpha is the angle made by the ends of the loop at the center. Now you see that it is a semicircle, so this angle is pi. So I'll write this. So I am getting mu 0 I by 4 r. This is the magnetic field produced by a semicircular loop at the center. Okay, clear? This is about the theory. Now we will go to the type of problems. First we will discuss the type 1. Linear part of a wire are very long. That means in this diagram, this is the linear part is very long and is parallel to the x-axis. Okay, then the semicircular portion of radius r lying in the YZ plane. In the YZ plane, the semicircular loop is lying. Okay, then find the magnetic field at the point O. Okay, So this is the problem. So they given us the linear portion. These two are the linear portion. I am going to split this loop is in two sections. This is a 1, this is a 2, and this is a 3. Okay, this 1 and 2 are infinitely long. Sorry, 1 and 3 are infinitely long, and the 2 is a semicircle. Okay, then this semicircular loop is in YZ plane, and the long wires, that is 1 and 3, is parallel to x-axis. Okay, so the magnet field at the point O is due to the magnet field due to two linear portion, that is B1 plus B3 plus magnet field due to semicircular loop. Okay, so that is B2. First of all, I am going to find out magnet field due to a semicircular loop, this semicircular loop. Okay, magnet field produced by a semicircular loop formula is mu 0 I by 4r. Here the radius is r. Okay, and what about the direction? Direction can be found out by right hand rule. So I am curl my palm in the direction of current, then the magnet field is going into it. Okay, this is in YZ plane, so the magnet field is going into it. That means in toward the x-axis, that is the minus x-axis, going into it. So I am giving the direction is minus ik. Okay, then next we will see the magnet field produced by B1. Okay, that is this straight portion. Okay, so magnet field produced by an infinitely long conductor, that is the formula is mu 0 I by 4 pi r. R is the distance from the current carrying conductor to the point. Okay, here the distance from the current carrying conductor to the point O is r. Sin phi 1 plus phi 2. What is phi 1? Phi 1 is the angle made by the one end of the conductor to the point. That means here this end to O. So this is infinitely long. So phi 1 we can take it as 90 degree. Okay, then phi 2 is angle made by the other end to the point. So here this point, this end to this point, that is 0 degree. Okay, then now you see sin 90 value is 1. So sin 0 value is 0. So mu 0 I by 4 pi r. This is the magnitude. What about the direction? Direction of the magnetic field produced by a straight current carrying conductor can be found out by right hand thumb rule. Place your thumb in the direction of current, then curled fingers give the magnetic field. So you see here it is going into and here it is coming out. So it is going into it. This current carrying conductor is in the x-axis, it is parallel to x-axis. So you see that it will produce going into it, that is coming downward. So this is minus z-axis. So we can say that minus k cap is the direction, this is the B1 direction. Okay, what about the magnetic field produced by the B3? You see the B3 also similar to B1 portion. Okay, one end of the B3 also making an angle 0, other end of the B3 also making an angle 90 degree, and the distance from the O portion also r. So the magnitude is mu 0 I by 4 pi r. We will see only the direction. This is the B2 and this is B1. We will see the B3. So direction of the magnetic field can be found out by right hand thumb rule. Place your thumb in the direction of current, then the curled fingers. Here you see that the palm is going into it. So here this is the direction B3. B3 also in the same direction. So I can write it as minus k cap. Okay, clear? Then now you see these two are in the same direction. Then so we will substitute in this equation. So what about the B1? B1 is equal to mu 0 I by 4 pi r minus k plus B3 is mu 0 I by that is mu 0 I by 4 pi r minus k plus b2. b2 is how much? Mu 0 I by 4r minus I. Okay, then from these two add, you will get, these two are in the same direction, so you can add it. So what you will get, that is mu 0 I by, all the time 4 pi r I am taking outside, mu 0 I by 4 pi r I am taking outside, and the minus sign also I am here. Then 1 is remaining, here also 1 is remaining, so 2 in which direction? K cap plus, in this what is remaining? 4 pi I am taken, so pi is here and I. This is a magnetic field at the point O. Okay, this is about the type 1. Type 2. Find the magnetic field at C. They are given a loop. We need to find out the magnetic field at the C. And consider this loop as two straight conductor and two semicircular loop. Okay, then the magnetic field at the C is due to two straight conductor magnetic field, that is magnetic field due to PQ plus magnetic field due to RS plus magnetic field due to two semicircular loop, that is the magnetic field due to PS plus the magnetic field due to QR. Okay, so first of all I am going to find out the magnetic field due to PQ and RS. Magnetic field due to PQ. So you consider it. This is a straight conductor. For this straight conductor, this point C is along the axis. So magnetic field at a point along the axis of a straight conductor is 0. So this is 0. And similar to the RS also, the point C is along the axis. So the magnetic field due to RS also 0. Okay, then the magnetic field due to PS we will find out. The magnetic field due to PS. PS is a semicircular loop. The magnetic field produced by the semicircular loop is mu 0 I by 4r. Here the radius is r2. Okay, what about the direction? Direction can be found out by right hand rule. So I curl my palm in the direction of current, I will get the direction is going into it. Okay, so this is the direction of magnetic field. Then the magnetic field due to QR. Okay, that is also semicircular loop. So magnetic field is mu 0 I by 4 into the radius. That is the radius is R1. So what about the direction? Direction can be found out by right hand rule. Curl the fingers in the direction of current, then the direction of the magnetic field is upwards. This is the magnetic field direction. So the net magnetic field BC is due to magnetic field due to these two portion plus these two portion. This is 0. These two are in the opposite direction. So the net magnetic field is higher value minus lower value. Which is the higher one? Here the denominator is lowest for this portion. So this is the higher one. So we can get the mu 0 I by 4r1 minus mu 0 I by 4r2. From this mu 0 I divided by 4 into 1 by r1 minus 1 by r2. Okay, this is the net magnetic field and the direction of the magnetic field is this direction, that is coming out. Okay, clear? This is about the type 2. Type 3 problem. A battery is connected between 2 points A and B on circumference of a uniform conducting ring of radius r and the resistance is capital R. One arc of AB of a ring subtend an angle theta at the center. The magnetic field at the center of the ring is. 4 options are given. So what is the meaning of the problem? So there is a circular ring is there. Okay. In that ring of radius r, the 2 points AB is connected to a battery. Okay. This AB is making an angle theta at the center. And consider O is the center. There is a battery is connected. And consider the positive terminal is connected to A and the negative terminal is connected to B. Okay, clear. Now you see that this arc AB, this are downside arc, that is I am consider the first arc. This is the second arc, I am consider the top arc. Okay, this is the second arc. This arc is and this arc is parallel to this voltage source. So the current I comes from the positive terminal. Here it is split into two. The I1 current passes through here and I2 current passes through here. They again combine it and come to negative terminal. Okay. Then we need to find out magnetic field at the center. Okay. Magnetic field produced by a circular loop, that is an arc. Okay. At the center is B is equal to mu 0 I by 4 pi r. I is the radius into theta. Clear? Okay. Let me see if the angle varies. Is there any change in the B value? Okay. So look at here. Mu 0 is constant, 4 is constant, pi is constant, and r is also constant. R is the radius. So I can say that the B is directly proportional to I theta. Okay, then what about the current? Current formula is V by R. I consider V is the voltage source, then current is I is equal to V by R. What about R? R is the resistance. Resistance formula is rho L by A. Rho is a constant because material is same. And what about the L? L will vary. What about the area of cross section? It is a uniform wire like that it is given. So L, A will not vary. So I can say that here I is inversely proportional to resistance. Here R is directly proportional to length. So now I can say that I is inversely proportional to length. Okay. Then from this, what about the theta? Theta I will get it as arc length divided by radius. Arc length I am taking as L and the radius is R. So this R is a constant. So I can say that L is directly proportional to theta. So now I can say that I is inversely proportional to theta. That is I theta is a constant. I theta is a constant. Okay. That means you see that if the current flowing through the first loop is I1 and the angle is theta, that is equal to the current through the second loop I2 into the angle made by the loop is 2 pi minus theta, because total angle is 2 pi, in that theta is remaining. Okay, so this is constant. Okay, please remember this. By using this we can find out the magnetic field. Okay, clear? Then now you will apply. What is the magnetic field at the point O due to first loop, that is of B1, that is equal to mu 0 I1 divided by 4 pi r into theta. Okay, what about the direction? Direction can be found out by right hand thumb rule. Place your thumb in the direction of current, curl the fingers. That means I am getting here it is going into, here it is coming out. So this is the B1 direction. Okay, so from this is coming out. What about the B2 direction? B2 you will get this. So B2 is equal to mu 0 I2 divided by 4 pi r into, what about the angle? That is 2 pi minus theta. Okay, the direction can be found out by right hand thumb. Thumb in the direction of current, curl the fingers. Here it is going into, here it is coming out. So the B2 direction is like this. So B2 is going into it. Okay. So in this 210, the only variable factor is I1 and theta. That is already equal like that we got. So magnetic field at the O is equal to what? We will get B1 plus B2. Okay, B1 plus B2. What about this B1 and B2? This B1 and B2 are equal and opposite direction. B1 is coming out and the B2 is going into. So the net magnetic field at B is equal to what you will get, that is 0. So which is the correct option? This is the correct option.
Thank you for watching the video. Please subscribe my channel. If you like this video, please put like